The absolute heartbeat of electronics. Look, before you can build anything, or fix anything, or even really understand any circuit, you have to get a solid grip on two core ideas: voltage and current. You can think of them as the why and the what of electricity. Once you get this, I promise everything else just starts to click into place.
So before we can even dream of analyzing some complex circuit diagram, we've got to start with the most fundamental question there is. What is that invisible force? What's the electrical pressure that actually makes everything happen in the first place? Let's figure that out.
So here's our game plan. First, we're going to dig into the potential, that stored energy we call voltage. Then, we'll check out where it actually comes from. After that, we'll look at the flow that this potential creates, and that's current. And finally, we're going to tie it all together and see this really elegant cause and effect relationship that literally powers our world. Okay, let's dive right in. We're starting with this idea of electrical potential energy. And in the world of circuits, we have a much simpler name for this: voltage.
Now this is a really critical distinction. Voltage isn't the electricity that's moving. No, it's the pressure that's just waiting to make it move. You know, it's like a coiled spring or the water held back by a dam. It's pure potential, just stored energy, ready and waiting to be unleashed.
And here's the beautiful math behind it. Voltage is simply the amount of energy available for a certain amount of charge. So when we say 1 volt, what we're really saying is there's 1 joule of energy, that's our standard unit for work, ready to push 1 coulomb of charge. And a coulomb, that's just a huge group of electrons. So voltage is really a measure of potential per unit of charge.
You know, this water tower analogy is just perfect for this. The height of the water creates pressure at the bottom of the tank, right? Even if the tap is closed. Well, that pressure? That's the voltage. So a 9-volt battery has way more electrical pressure than a little 1.5-volt battery, just like a taller water tower has more water pressure. It is all about the potential to do work. Okay, so if voltage is this potential energy, where does it come from? I mean, what are the real-world things that act like that water pump, creating the electrical pressure we need in our circuits? Let's take a look at some of the most common sources. Here are a bunch of the usual suspects for direct current, or DC, voltage. Now, what's really important to remember is that these devices don't create charge. The charge, the electrons, they're already hanging out in the wires. All these sources do is provide the energy to get those charges moving. Let's start with the one we all know, the battery. What's happening inside is basically a tiny, very controlled chemical reaction. This reaction forcibly separates charges, creating a pileup of electrons on the negative side and a lack of them on the positive side. That separation is the voltage. It's like a little pocket-sized power plant, converting chemical energy into electrical potential. Now, a fuel cell, it works on a pretty similar principle, but instead of using up chemicals that are already sealed inside like a battery, it's constantly fed an external fuel, something like hydrogen. Just think of it like a battery that never runs out, as long as you keep filling up the tank.
And then we have solar cells, where the energy source is, you guessed it, light itself. When photons from the sun smack into a solar cell, they basically transfer their energy to electrons inside the material. This little energy boost is what creates the voltage, giving us the push we need to drive a current.
Okay, so we've established the push. That's the voltage. So what happens when we actually give that push a path to do something? Well, it's time to talk about the flow. In electronics, we call that current.
This is the action. This is what's actually happening. If voltage is the potential energy stored in our water tank, then current is the actual water flowing through the pipe when we open up the valve. In a wire, it's the organized movement of free electrons, all kind of drifting in the same general direction.
And the formula for current measures exactly what you'd think it would: how much and how fast. It's the amount of charge, Q, that passes one single point in a wire divided by the time T it takes to do it. This gives us the amp, or amp. So 1 amp literally means 1 coulomb of charge is flowing past a point every single second. It's a rate, just like gallons per minute for water.
So the crucial link is this: the voltage we apply across a wire creates something called an electric field. This field puts a force on all the free electrons, pushing them away from the negative terminal and pulling them towards the positive one. This organized net movement of charge, that's what we measure as electrical current.
All right, let's bring this all home and really nail down the distinct but totally inseparable relationship between these two fundamental quantities of electricity.
This right here, this brings us to the most important takeaway of the day. Voltage is the cause. It's the electrical pressure.
Current is the effect. It's the resulting flow of charge. See, you can have voltage without current. Think of a battery just sitting on your desk. But you can never have a current without a voltage there to push it. They are fundamentally linked as cause and effect.
And this leads us to a really great question. Because in any real circuit, there's always something getting in the way, something that impedes that flow of electrons. This opposition is the third critical pillar of circuit analysis, and it's the very thing we'll be exploring next time.